Bismillahirrahmanirrahim. Today we'll be doing lecture number 5A, Heat and Work. Before we start our lecture, let's have a little bit review of what we have done in our previous lectures. If I'm saying like starting from lecture number 1. So we did some basic concepts. We did said something about the system and surrounding. We did define some open system and closed system. And then obviously we did define the state of those system, and we said like the state can only be defined when the system is in equilibrium. Yes, we did said something about changing from that equilibrium, and that was actually in a process. The process is the change in the state of the system. For the change in the state of the system, um, we define another term called as quasi-equilibrium process, which is sufficiently slow process. We define as sufficiently slow process, and that was helpful to define the path of the process. From this whole thing, we did define the equation of the state of the system, and yes, we did something. We did write something about the ideal gas equation and non-ideal gas equation, and when we did use some property tables and etc. etc. So today's topic is again heat and work. Now the question would arise like if we are saying like changing the state of the system. So how do we change the state of the system? So the changing in the state of the system is with the help of energy, which would be in form of heat or either work. So there are two different kind of energy. One would be the heat energy and one would be the work energy. So heat and work are two different way of transferring energy from one system to another. Heat is transfer of thermal energy between the system, while work is transfer of the mechanical energy between the two systems. During these interaction, as we said, like in a process as well, the equilibrium or quasi-equilibrium process would be necessary to if we want to define the equation that would relate to the system properties. As said, like system would be only defined when we are talking about the equilibrium or quasi-equilibrium process. Heat can transfer into work, and work can be transferred to the heat, but they aren't the same thing. Yes, we would be defining the same thing in the first law of thermodynamics and obviously in the second law of thermodynamics. The first law of thermodynamics relate the heat and work both contribute to the total internal energy of the system, but the second law of thermodynamics, this limits the amount of heat and that can be turned into work. Yes, we will be studying these things in the later lectures. So what is heat? Heat is an energy that can be transferred due to temperature difference only. So just the word few things. It Heat is the energy, form of energy, which can be transferred due to temperature difference and only. That's what actual different terms are there. So that means like we would be defining heat only and only when there is a temperature difference between the bodies, and it can be only and only defined when it is transferred. Without anything like this, without any of these terms, the heat cannot be defined. So heat, yes, as we said earlier, heat is the form of energy which can be used to change the state of the system when, or which we can say like heat is a transfer. Heat transfer can alter the system state. Bodies that does not contain heat. Heat is only identified when it crosses the system boundary. As said a little earlier, heat is only and only defined when it is transferred. Heat cannot be defined when it is not transferred. Just say, for example, somebody say like, okay, I've got a body which has got the temperature 50 degrees centigrade and 50 degree, or let's say 500 degrees centigrade. So the question would arise whether this 500 degrees centigrade, does it contain heat or not? So the only thing like if there is a heat transfer from the system to the surrounding, then there is possibility like the heat would be defined. But if there is no heat transfer from the system to the surrounding, then the heat is not defined. For example, if the surrounding temperature is, let's say, 500 degrees centigrade, 50 degrees centigrade, so let's say heat would be defined because heat would be transferred from this 500 degrees centigrade to 50 degrees centigrade, and yes, we can define heat. But let's say on the other hand, if the surrounding is same 500 degrees centigrade, would you define the heat then? No, heat cannot be defined because the heat is not transfer, which means like heat is not transferred from the system to the surrounding, heat is not exchanged, so obviously the heat is not defined. So the amount of heat that is needed to go from one state to another state is a path dependent. If you remember, as even in this initial starting of this lecture, I said like what is actually the path? Path would be actually we call it as a process. What is the process? What it actually how which process the system is going from one state to another state. Say like the amount of heat going from one state to another state is actually a process dependent or a path dependent. Let me have an example. Let's have an example, and let's have an example of a pressure cooker, or let's say we are heating a water, and let's say heating a water inside a pressure cooker, and let's say we are supplying some heat to it. So what would happen, like when we supply starting heat, the water would start boiling, and this it will be actually raising the temperature and start boiling. And let's say put a lid on that pressure cooker now. What would happen right now? The amount of amount of time that would be taken by this water to be heated would be less. What actually I means to say, like the amount of the water would boil quickly. So what actually has been changed? We have not changed the amount of heat supplied, we have not changed anything else, but what we have done is actually initially there was no lid on the pressure cooker, and now what we did, like in a second point, we actually put some lid on it. So if you put on lid on it, so what we are saying, like we have increased a little bit pressure. So that means like the amount of heat that was supplied from the, let's say, heat source to a pressure cooker was actually the pressure dependent. So that in a simple way, what I'm again saying, like the amount of heat that is needed from one state to another state is what we call it as a path dependent. That means like process dependent. So that's it. Actually, we can say like in one process we will be having different amount of heat, while in another process we will be having different amount of heat. Now the adiabatic process, what we call it, adiabatic process in is the one in which there is no heat transfer. So in adiabatic process there is no heat transfer into the system. That can also be like there is no heat transfer at all, like we have actually not supplied any heat source to it, or it might be like the process was so quick enough that the time actually it would take, or the time required for the heat to transfer was so less that heat was not transferred. For example, if you have got a hot plate, let's say of a 5000 degrees centigrade, and if you just tap it very quickly, so that means like when you're tapping it very quickly, so the heat transfer would be not there. So if it is not there, that means like the time actually was so less that you cannot feel the heat in your hand. That means like the adiabatic process would be either there is no heat at all, or the amount of time was so less that the heat was not transferred at all. So before going to the next topic of work, let's have another idea, and that idea is actually another law, and that is actually the Zeroth Law of Thermodynamics. So laws of thermodynamics are based on some observation, and that observation lead to something that is always true, I would say. Like, so with the material so far we have discussed, let's discuss the Zeroth Law of Thermodynamics itself. Zeroth Law of Thermodynamics defines some or based on two such observation. First observation, let's say, if the body is in contact with thermally contact with another body, let's say body A is in contact with another body for sufficiently long time, there would be no further change take place, and there would be actually some thermal equilibrium between these two bodies. The second observation, if a body A is in thermal equilibrium with body B and body B is in thermal equilibrium with body C, that would mean like A is in thermal equilibrium with C. In other words, if I'm saying like if temperature, a property called as temperature T1 or TA is equal to TB and TB is equal to TC, that would mean like a property temperature TA would be equal to property temperature TC. And obviously, there will be no heat transfer from TA into TC or TA into TB. So in other words, a property, we did define two things in it. These closely connected ideas define two different things. One thing or one observation, we call it as the thermal equilibrium. So that means like body A is in thermal equilibrium with body B and body B is in thermal equilibrium with body C. So observation was the thermal equilibrium, which lead to the equality of the property. That property is called as the temperature. So in other words, the zeroth law of thermodynamics defines two things. One, thermal equilibrium, and that thermal equilibrium is defined with a property called as temperature. So in any of the law of thermodynamics, we would be defining some observation, and that observation would be defined with a certain property, and that property can be any property then. So formally, zeroth law, there exists in every thermodynamic system an equilibrium, a property called as temperature. An equality of temperature is necessary and sufficient condition for thermal equilibrium. The zeroth law thus define a property called as temperature and describe its behavior. And one just more thing, why this thing is called as zeroth law of thermodynamics. So a very simple answer, and that simple answer is correct. The first law of thermodynamics was defined before this law of thermodynamics. So to name it, it was named as zeroth law of thermodynamics. So let's say if we have got another law which need to be defined before zeroth law of thermodynamics, so obviously your mind would be saying like, okay, why not to just call it -1 thermodynamic law? So something like this. And why we need to define this thing before the first law of thermodynamics? I did say like something about the thermal equilibrium, and in above thing we did say like the heat transfer can change, heat can be only transferred due to temperature difference. So if there is a thermal equilibrium between the system, so there will be no heat transfer between the system. When there is no heat transfer between the system, then there is no work done, which would be actually our main observation in the first law of thermodynamics. So obviously, for first law of thermodynamics, we need to define the law, and that is called as zeroth law of thermodynamics. You might be familiar with the different temperature scale. Um we know the temperature scale called as Kelvin scale, and that is based on the absolute scale of degree centigrade. If you remember that one from your sorry for that, if you remember from your previous thing, yes, that was a temperature scale of degree centigrade. So if you add 273.15 into degree centigrade, you would be actually having degree Kelvin, or simply Kelvin. Um, that is in SI unit. So if you're looking for the English unit, which define the temperature in terms of degree Fahrenheit, the absolute temperature scale for degree Fahrenheit is actually degree Rankine. So if you add 459.9 into degree Fahrenheit, you will get the temperature, absolute temperature, which would be actually called as the degree Fahrenheit temperature. So this is what actually we have got. We have got two temperature scale, degree centigrade and degree Fahrenheit. Absolute temperature scale of degree centigrade is degree Kelvin or Kelvin simply, and absolute temperature of degree Fahrenheit is Rankine or degree Rankine. Now let's move to another form of energy, and that energy is called as work energy. Uh, I'm calling them both the energy. If you can imagine or if you remember, the unit of both of these energy are in kilojoule. So these are different form of energy we will be looking at. So another mean apart from heat for changing the energy of the system or changing the state of the system is called as the work. So in a simple classical definition of work in mechanical work is the mechanical work defined by the force into displacement. In other words, force into displacement is what we call it as a work done. For a finite work, which would mean like from state 1 to state 2, the work done would be equal to force from 1 to 2. Work done from 1 to 2 would be equal to force into displacement from state 1 to state 2. Yes, we can say like this is actually a mechanical work, and displacement x would be definitely again in a mechanical displacement. But in a simple word, the force can be any force and displacement can be any displacement. Like in a push-pull work, we have got different force, different displacement. For electrical work, we have got different force, we call it electrical force. We have got different displacement, we call it as charge displacement. For a magnetic force work, that might be magnetic flux or something, we might have got different displacement for magnetic flux. For chemical force, we can have different concentration and displacement would be from one form to another form or something like this. For surface tension, for a elastic word, etc., etc. So what does that mean? Like in a simple classical word, the force can be anything and displacement can be anything. So this is just what we call it as a force into displacement. So we will be sticking towards this one, and then obviously we'll be defining our own definition of the work done. So in defining the work in a simple work, in a simple way, we will focus on the effect of the system and the surrounding obviously. So the work done would be positive if the system is doing some work done on the surrounding. So if the system is doing some work done on the surrounding, we would call it as a positive work. For a negative work, when the work done is on the system, we will call it as a negative work. You might use on different books, different thermodynamic book, different chemical book, and it might be different in that. It might be the sign convention might be different in different books. It might be the same reason. Like if I would say like in your chemistry book, if it would be the work done was defined positive when we were having the work done by on a system by the surrounding. So when we have got work is done on a system, we define it as a positive. In a chemistry we call it, in that case it is the energy added to the system. If I'm saying like the work was negative in your chemistry book, when the work done was by the system on the surrounding, in that case they would actually assuming they were saying like as energy is leaving the system, so we would call it as a negative work. But yes, in our own convention, what we would be saying like we would be defining the work done when the system is doing work done on the surrounding, and we would be defining the negative work done when the system when the work done is on the system by the surrounding. So, let's say for example, in figure 5.2, we have got a gas system, which is actually simple. In other words, imagine piston and cylinder, what we have done till now. And the piston is a movable piston, and it is actually having a displacement of L, and the work is done on the surrounding. Before going that one, that area, let's say that the pressure inside the system is PS, and the pressure outside the system is Px, external pressure, I would call it. The area of the piston is A, let's say, and the displacement is actually dl. So this would be something I would be looking for. So in the top bit, what we have said earlier, work done would be force into displacement. So work done on the surrounding would be the force that would be acting on the surrounding, and that would be the displacement which would be actually acting on the surrounding as well. Let me just divide with the area and multiply with the area. So that means like force of the surrounding per unit area, and area into dl, if I would say. So in that case, force per unit area multiply by dl, and obviously that's what I'm saying. That would be actually the pressure. Force per unit area would be pressure, and area into displacement would be volume. So my new definition of the work done would be the pressure into the volume change. So that would be something like this. So this is actually work done on the surrounding actually. So the work done on the surrounding would be the pressure of the surrounding into the volume. And if you can imagine, the work done of the work done would be equal to Px into dV. For the total work done from changing from volume V1 to volume V2, we would be having integral from V1 to V2 Px dV. Now the question is, pressure is Px over here, and why is the pressure Px instead of Ps? In word term, what I'm saying, like, the work is done by the system on the surrounding. So it was the change in the pressure of the system which was responsible for the change in the volume. It is not actually the pressure Px, I would say, like, it is the pressure Ps that would need to be considered. But let's say whether our definition was wrong somewhere or not, let's check it. Our definition, which had come up like this, it is actually work done would be equal to Px dV. Let's say, for example, in one of the condition, if I would write Px is equal to 0, which mean like outside the piston, the pressure is 0, or outside the piston, the pressure is, or it is vacuum somewhere. And you might have noticed this vacuum if you are talking about something like in a space, or if you're talking about something like in a moonwalking or something. So if I would say, like, if you have seen moonwalking, and if you have seen some astronaut working in a space, you might have noticed that astronaut is trying to do work on the surrounding, but as there is external pressure in the surrounding is 0, so the work done on the surrounding is not there. In other words, if I would say, like, okay, let's have another example. If I'm walking on a let's say rigid surface, and if I'm walking on a rigid surface, obviously that means like I'm pushing the surface, and the surface is pushing me back, so I am actually moving. Let's say if I'm walking on a little bit softer surface, let's say for example sand, so I am actually making more efforts, and I am actually struggling with my walking. That mean like what I'm saying, like, they whatever I am doing work done on the sand, it is actually not reflected back to me. That mean like I am having a little bit difficulty in my walking. Let's say I have another example. Can I walk on water? As there is, yes, I am actually doing some work, I am actually applying some pressure, but as there is no external pressure on myself, so I am having a very difficulty in walking on the water. And let's say take it to the air, and obviously take it to the vacuum then. So the more the the less pressure is outside, it will be really difficult for the work done to be transferred to the surrounding. In other words, this term dW would be equal to 0 if Px is equal to 0. Now the question is very simple now. Whether the system was not doing some work done or not. That means like if W is equal to 0, does that mean like the system itself was also not working? No, the system was working, but it was not reflected outside. In other words, the astronaut was trying to work on his surrounding, but it was not reflected. Or if I say like I want to move on water, but definitely there was no pressure externally. So obviously I could not do my work. So that means like, can I just say again, I am more interested in the work done by the system on the surrounding. If that work done is transferred or not transferred, I'm not interested. Or if I'm saying like I'm not so worried about that thing, but what I'm interested in, like whether the system has done some work on the surrounding or is there, and I'm actually quantifying the work done by the system on the surrounding. So how do we do it? If we consider PS is equal to Px. So if we consider PS is equal to, sorry, I'll just rub it down, PS is equal to Px, then in that case, I would be saying the work done is by the system on the surrounding. In other words, the same amount of pressure change in the system is the same amount of pressure that would be expected to change in the surrounding. Then in that case, I would be replacing this work done by the system on the surrounding. So that would be case. So when I would, now the question would arise, at what point I can consider PS is equal to PX. One of the main thing would be if I consider this to be a frictionless piston. Let's say if it is frictionless piston, so whatever the change in this one would be equal to change in this one. In other words, if I say like if there is some friction in here somewhere, so that means like whatever the change inside the PS would definitely not equal to the change of the PX. So that means in my term, PX would be only and only equal to PS when there is no friction in the piston itself. Now the second condition would be when the system is moving slowly. In other words, let's say if you have seen some syringes or something, if I'll say like, okay, like let me say it again, like let's say if you pull this piston too quickly, if I'll say like, if you pull this piston too quickly, then there would be some resistive forces which would be actually pulling this on the opposite side. So like a syringe, if you remember a syringe of the medical syringe, if you pull it a little bit quickly, so that means like there is a certain resistant forces which is actually pulling the piston in opposite direction. So that means like if you are doing it very fast, so that will actually give you a little bit different pressure change. In other words as well, if you are pushing this very quickly, if you are pushing this piston very quickly, so that would mean like there would be some resistant forces which would be actually pushing this piston in this direction as well. So what I mean to say, like, if you are doing it very quickly, there would be some resistive forces again, and that can be in terms of vacuum, and that can be in terms of some, you know, some eddies or something. So if you're doing it like this, so there would be some resistant forces, and that means like PS would not be equal to PX. So in that case, what you need to do, again, as I like, what you need to do, you need to pull the piston very, very slowly. Or if I'm saying like you have, the process should be very, very slowly. So that case, if you want to, know, that mean like the process should be the quasi-equilibrium process. So that would be quasi-static process. So we define two conditions. Let me rewind it again. We define two conditions. In order to have PS is equal to PX, the change, which is actually the change in the pressure inside the piston, should be equal to the change in pressure outside the piston. For that case, the process must be frictionless and the process must be slow. In other words, the process must be quasi-static process. Quasi-static process mean like whatever the change, a small change in a pressure can be altered or can be, let's say, negate, and that mean like this can be equal to this thing now. So let me put that back into the above equation, which was this equation for us. So if you are putting that in above equation, that would come up as px dv, and that is px dp, something like this, and we would be having ps dv plus dp dv. As we say, like, this dp is sufficiently small. If I remember from the quasi-equilibrium process, is this dp, and then obviously another small amount multiply by another small amount, so that would be very, very negligible amount, and that mean like this would be equal to this thing now in a simple way. Now what is this work done now? This is the work done by the system on the surrounding, and that's what actually we were interested in. Now we did define two conditions in it. The process was frictionless and it was quasi-static. Another term we did define the process is reversible process. Any change that would occur can be actually reversed. The system and the condition for reversibility was the system and surrounding will return to its original state, and obviously if we apply dp very small, any change in that dp, if we negate it, that would be not effective. So that means like for a quasi-equilibrium process, for a quasi-equilibrium frictionless process, the work done by the system and on a surrounding is equal to PSD. And that's what actually we are doing now. So in case of free expansion, I did explain this thing and so on and so forth. So we have got this equation, and that in terms of mass. Over here, it's like for a simple compressible substance in a reversible process, the work done can be represented by area under the curve on a PV diagram. Let me come back to this thing later, and let me move forward and then obviously explain a little bit more detail, and then I'll be coming back to the same question or same concept. So key point to be noted: property not only depend on the state, but work is a path dependent property. Depend on which process we have followed, and obviously we will be looking at later on this one. We say that work done from 1 to 2, that means like from state 1 to state 2. If we are defining, then we must define the path of the work done as well. Path, again, I'm saying like path mean like process. For irreversible work, for we have got different equation. This equation, which was PdV, was only and only valid for the reversible work. So for the irreversible work, the work done must be either given or must be we can find on a different other method. So this is what actually a little bit of the work done. Let's move forward with another example, and obviously we have left something up there and we will be coming back to it later. Work done on a too simple path. I'm saying again, what do we mean by path? We mean by path, the path mean like the processes. So work done, consider figure 5.5, which shows system undergoing a quasi-equilibrium processes, which can be calculated work done interaction by PdV, obviously. So let's say I've got two paths. I'm going from state 1 to state 2, and let's say I am actually applying two paths. One is called as path A and one is called as path B. So we have got two works, path from 1 to 2. One is actually in a path A and one is in a path B. What is actually path A? In path A, I'm moving from volume V0 to 2V0. First, I'm moving in a constant pressure. I have got a pressure of, let's say, I will explain again. I've got a pressure P0 and 2P0, and I've got a volume V0 and 2V0. So in a first path, which is path A, I'm going from state 1 to, let's say, A, while keeping the pressure constant and changing the volume from V0 to 2V0. Then I'm keeping the volume constant and just dropping my pressure from A to 2, and that is what actually I would call it as a path A. In a second path, that which is actually path B, I'm first dropping my pressure from 2P0 to P0 while keeping the volume constant, which is actually volume V0. While in other words, in a second phase, I'm keeping my pressure P0 constant while changing the volume from 2V0 to V0 to 2V0. So that means like in a first path, I'm changing the volume, keeping the pressure constant, changing the volume, keeping the pressure constant, and then keeping the volume constant, changing the pressure. That is path A. While in second path, I'm first changing the first changing the pressure, keeping the volume constant, and then I'm keeping the pressure constant while changing the volume. So this is my different path. So let's say work done in two different parts. If I'm saying like, and a simple equation for the work done, that's what actually up there and or over here, that is actually PdV. So that means like work done in, let's say, work done in a path A would be equal to PdV in a path A. What I'm saying like, or how do we calculate it? So let's say, let's say path A. First, I'm changing from this place to this place. So that means like keeping the pressure constant, which was equal to PV0, while changing the volume, which was 2V0 minus V0. So that means like change the total volume change was 2V0 minus V0. Plus, I have got another over here, another leg over here, like we call it as process. So you'll be understanding it. Now, if you remember, the volume is constant. So if the volume is constant, so that means anything multiplied with that thing would be zero. In other words, if you remember, while if you do not change the volume, there would be no work done. If there is no displacement, there is no work done. So another way I'm saying like the total work done in a path A would be equal to 2P0 2V0 minus V0, and that's equal to 2P0 into V0. So work done in a path A is 2P0 into V0. Let's have another one. Work done in a path B. Work done in a path B in the same for the same equation. So work done in path B would be actually I'm changing the pressure from 2P naught into P naught, but keeping the volume constant. So that means like in the first leg I would be having 0 work done plus then I have got 2P naught pressure and then I'm changing volume. So to P naught, sorry, P naught into changing the volume to V naught minus V naught, that would go to P naught into V naught. So that means like work done in a path B would be equal to P naught into V naught. So that's been summarized over here in this equation somewhere here. Let me rub it out. So we have got work done in a path A is equal to 2P naught V naught and work done in a path B equal to 2 sorry P naught into V naught. Even though we have changed state from 1 to 2, I'm going from work done from 1 to 2, but I'm changing the state in two different processes. One, I'm keeping the pressure constant, changing the volume, and then keeping the volume constant, changing the pressure. And another part, first I'm changing the pressure. So yes, changing the pressure, keeping the volume constant, and then changing the volume, keeping the pressure constant. So in these two different processes, I have got two different kind of work. So that means like work done is a path dependent property. So when we say like work done from 1 to 2, we must specify the path of the system. So work is a path dependent property. Again, I'm saying work done is a process dependent property. Now it's like above there it was written somewhere here. For a simple compressible substance in a reversible process, the work done can be represented by the area under the curve on a PV diagram. So we have got the PV diagram over here. So it say like the work done is equal to the area under the curve. So let me say like area under the curve of path A, let's say, which is this one somewhere here. So if you want to find the area, so that means like this like which is 2 V naught minus V naught multiplied by this height which is 2 P naught, that is equal to 2 P naught into V naught. This is the one. Let me change the color. On the path B, like if I'm saying like this, like so the area under the curve is this much. So that is because area under this line is 0. So obviously only on this line there would be some area obviously. So if I'm saying like area under this one, so that means like again 2 V naught minus V naught multiplied by this V naught. So that means like V naught over here that equal to V naught V. So that means like that was work done in A and that was work done in B, if you remember. So in a simple way, this was 2P naught into V naught was the work done in a path A, and this sorry for that, and this P naught into V naught, which is area under the curve of path B, is the work done in a path A. So in other words, what actually it say like for a simple compressible substance in a reversible process, we did say like reversible process because it was quasi-equilibrium process, it was frictionless process. The work done can be represented by the area under the curve of a PV diagram. So that's how we define the work done. So the area under the curve of a PV diagram is equal to the work done in a process. So in a simple way, if you find the area under the curve, you can find the work done. Let's go to another example, example number 2, and that is example work done during the expansion of the gases. Let's say expansion of the gases, and consider quasi-static isothermal expansion. So the process is quasi-static. We know that it would be actually the formula we have used only was actually for the quasi-static process, but the process is now isothermal as well of the thermally ideal gas from P1 to P1 V1 to P2 V2, which mean like that is expansion of the gas. Expansion would mean like volume would be changing from V1, which is less volume, to volume V2, and the pressure, which is actually P1, which high pressure, would be actually going towards P2, which is actually the lower pressure. So this is what actually it means. So that means like the work done would be actually work done during the expansion of the gases, and that expansion is isothermal expansion. So in other words, if you move towards the top one, the area under the curve. So if you want to find the area under the curve of this one, so definitely it will be a little bit difficult for you to find the area of this thing. Yes, you can divide this over here, and then obviously divide a small bit, which is actually we call it as the non-exact differential. And then if you want to do this thing, so that means like in a non-exact differential, you will differentiate this area, and obviously you can actually find the area under the curve of this PV diagram. But that's a little bit difficult now. So let's do with the equation of the thermal ideal gas, which is equal to PV is equal to nRT. Moving towards the our own equation, which was W is equal to T dV. So that means like uh, oops, sorry, not there. So let's say let's move toward other one. So W is equal to PdV. Um, from this equation, let's say from this equation, P is equal to nRT divided by V. If I'm saying like nRT or RT, you can imagine anything. And that V would be actually not specific in terms, if you remember that thing. P is equal to nRT. Put this P, value of P, into this equation. So that means like W would be equal to nRT by V into dV. Integrate it, and if you integrate it, so that means like integrating from volume V1 to V2. That means like V1 to V2, that would be nRT divided by V into dV. Now the point is the process was isothermal as well. So taking n out from the integral, because this is constant, taking r out from the equation because it's constant, and also taking t out from the equation because that mean like the temperature was constant. So that mean like PV is equal to nr, sorry, the nRT is out of the equation now. So nRT, we are differentiating between V1 to V2, dV by V. So that means like if you can differentiate it, you will come up with the equation W is equal to nRT log of V2 by V1. That is nRT log of V2 by V1. If you can imagine for the isothermal process, PV is equal to RT. Remember that thing? PV is equal to nRT. If you anyway, whatever you write it down. So R is constant, temperature is constant in isothermal process. So that means like PV is constant. So if PV is constant, that also means like P1 V1 would be equal to P2 V2. So that means like the product of PV on this whole line, pressure and volume on this whole line, would be constant. So if I can say like V2, just moving this one, V2 by V1 would be equal to P1 by P2 somewhere here. So that means like you have got another equation which is equal to nRT log of P1 by P2. You can actually move to MRT log of this one and so on and so forth. So you can change the above equation in your own form, and that would be actually for your own benefit. This is the process when we were actually, this was the process when we were actually doing the isothermal expansion. If there is, let's say, any other kind of an expansion, that is, let's say, polytropic expansion. Polytropic expansion is the expansion in which actually PV is not constant, but PV raised to power n, there is n which is actually power n on volume, is constant. That we will explain it later on if you need to. So that means like that is a process in which the on the line itself the pressure and the volume are changing differently, or the pressure and volume on the line is changing with the equation which is PV raised to power n, and n can be anything above, sorry, not one, obviously if you want to put the one in it, so that would be isothermal process. N can be anything, and based on that n the process can be different. That process is called as polytropic process. Make sure you just go to your book actually and just look at this equation which has been derived for the polytropic process, and you would understand a little bit more about the polytropic process as well. This equation is valid for any process except for n is equal to 1. For n is equal to 1, which means like we have got the process which is isothermal. For the isothermal process, we have got this above equation. So let me conclude it. In the start of the lecture, we did say like heat and work are two different kind of energy which are responsible for the change in the state of the system. So the question would arise, which is responsible in which condition? Whether the state in the change in the state of the system is there, the work is responsible or the heat is responsible. So before we answer that question, we should look at the system itself. For example, let's take an example of a resistive heater. This is what actually we have got in our home normally. Water heater, you just put the heater inside the water to heat the system. Let me say like there is a temperature rise in a system, which is T is higher. So we are changing the state of the system, which is actually the rise in a temperature. By supplying some heat to the system, which is Q from the heater, and that heater is actually getting some work done from the electricity, or if in another term we have got the electric work done outside. So now let's say the question again, so which is responsible for the change in the state, or in other words, which is responsible for the change in the temperature of the system? So let's say if I consider this to be my system, which mean like the boundary of the system is somewhere a little bit not including the electricity. So as the temperature is rising, we simply understand like the temperature is rising due to the heat supplied. Now I would complete this example. Now if I'm including this work done in it as well, so it's a same again, the temperature is rising due to the heat supplied in it, but the heat is actually transferring due to the work supply. So in other words, what I'm saying like the change in the state, which is change in the temperature of the system, is due to the electrical work which is supplied from the above. So let me conclude it again. That means like if your boundary is limited to this bit, not including, sorry, not including the work done, so that means like you are only limiting yourself to the heat transfer, and that heat transfer is actually responsible for rise in the temperature. But if your boundary is also including the work done, which is actually the electrical work, so obviously that heat which is responsible for the rise in the temperature, this heat itself is actually due to the electrical work. So in other words, it is actually the system definition which would define the change in a state of the system. I hope you understand these new concepts. Let me know if you have got any question in it. Thank you very much.